Hey class, let's finish up our last section for chapter 12, congruent and similar figures. So we're going to learn to identify congruent and similar solids and to use properties of similar solids also. So we're going to see one property with similar solids later. All right, so let's first define similar solids. Similar solids is when there are two solids are similar if they have the same shape and the ratios of their corresponding linear measures are equal. And when we talk about ratio of their corresponding linear measures, we're really just talking about scale factor. All right, and the one thing to note too is that all spheres and cubes are automatically similar. And they're similar because they have, well, think about it, spheres only have radii or diameters to deal with, and so those are always going to be similar. And cubes, their length, their width, and their height are all the same, so those are all going to be similar. All right, now let's talk about congruent solids. Congruent solids happen when corresponding angles are congruent, when corresponding edges are congruent, and corresponding faces are congruent. And the last thing that has to happen, volumes must be equal. All right, so now we know what a congruent solid is and a similar solid. So we're looking for, if it's a similar solid, it's going to have the same scale factor. If we're looking for congruent, it's going to have the exact same measures. And here's our other thing it says, is it could be neither. Remember, when it's neither, neither of those things are happening. So in these next few problems, if they're similar, we're going to state the scale factor. So let's just look right away. We have a height of 4 and a height of 6. Obviously, those aren't congruent, so we can right away think about not congruent. So we're either looking for similar or neither. So let's do some scale factors. Let's do the height first. So I'm just going to go the small one to the big one, 4 to 6. And we want to reduce that, because if we reduce that, that's the scale factor. So let's make sure that the base edge has the same scale factor to see if they are congruent. So 8 to 12, and 8 to 12 is going to reduce down to 2/3. So those two are equal. So these are similar figures, and their scale factor is 2/3. Now, if you can't reduce fractions in your head, you're going to want to make sure you know how to reduce fractions using your calculator. You might get a decimal. You want to make sure you know how to go from a decimal to a fraction on your calculator. If you don't, then you're going to want to go ahead and Google that and figure out how to make a decimal into a fraction on your calculator. All right, number 2, again, we're looking for similar, congruent, or neither. Right away, we can look at here, we have a base edge of 3 and another base edge is 1.7. So we can say right off the bat they're not congruent. So let's look at our width first. And those are the two that I have underlined. So I'm just going to go from the left figure to the right figure, 3 over 1.7. Let's just make this into a decimal first off. And if those decimals end up being congruent, then we'll look for scale factor. So when I compare my widths, I get a scale factor of approximately 1.76. And I want to leave it out to the second decimal place because of rounding might make it look like it's similar, but it's not. All right, let's do our length. Length. So now we're looking here at 6.2 and 3.4. Again, you want to keep the same proportion ratio. So we get, approximately 1.82. So right away I can see that these aren't congruent scale factors, so I can say that it's neither. If I wanted to prove my point more, I could go in and do the height also, but we don't need to. All right, number 3. State whether each pair is similar, congruent, or neither. So let's look here. Our radii are 5 and 6, so right away we see it's not congruent. So we're looking for similar or neither. So let's compare our ratio of our radii of 5 to 6. Can I reduce that at all? Nope, that's going to stay at that scale factor. of 5 to 6. And our slant height is the other measurement we're given. And we get 12 and 14.4. Now here's the one thing I want you to do is I want you to see if you can reduce this down on your calculator. Now it's got a decimal in it. So find out how to go from a decimal to a fraction and find out what this missing scale factor is. And let me know, is this similar or is it neither? All right, number 4. The cubes to the right are similar solids with a scale factor of 3 to 2. Find the surface area of each figure, find the volume of each figure. Well, they're cubes, so I know that it has a width, a length, and a height of 3, and a width and a length and a height of 2. So scale surface area, remember, is lateral area plus 2 bases, or perimeter times height plus 2 base areas. So if we consider this our base, the perimeter of that is going to be 12, and my height is 3, plus 2 base areas. Well, length times width, 3 times 3 gives me 9. Go ahead and plug and chug that on your calculator. And we get 54. All right, now let's do the smaller cube. So again, let's just use this here as our base. So the perimeter of our base is 8, and our height is 2. Plus, we have 2 base areas. 2 times 2 gives us 4. So we end up with 24. Now I just want to say that our scale factor is 3 to 2. So let's just see the scale factor of our surface area. So if we put 54 over 24 and we reduce that, we get a 9 over 4. That's our scale factor of, or that's our ratios of our surface area. Keep that in mind for when we talk about our next theorem. All right, the volume of each figure. Okay, so in our large cube, the sides are 3, and it's going to be 3 times 3 times 3, and we get 27. And in our small figure, it's 2 times 2 times 2, so we get 8. Again, I want to just set up 27 over 8. Can we reduce that at all? Nope. So this is our ratio of our volumes. Now look here. We have our scale factors 3 to 2. Our ratio of our surface areas is 9 to 4. And our ratio of our volumes is 27 to 8. Looking at that, look for a pattern. We're going to see that pattern and talk about it right now. Theorem 12.1 says if two similar solids have a scale factor of A to B, then their surface areas have a ratio of A squared to B squared, and the volumes have a ratio of A cubed to B cubed. So let's look back at our previous problem. Our scale factor was 3 to 2. When we looked at our area, our ratios ended up being 9 to 4. So see how that's 3 squared and 2 squared? And then our volume ratio was 27 to 8. That 27 to 8 is 3 cubed and 2 cubed. All right, so let's use that knowledge. If two similar cones have radii of 10 millimeters and 15 millimeters, what's the ratio of the surface area, key right there, of the small cone to the surface area of the large cone? So first we need to find our scale factor. So small cone to large cone, this is going to reduce down to 2/3. This is our scale factor. Now we want to talk about surface area, so we're going to take our scale factor and square it for surface area. So our ratio of our surface areas is 4 to 9. That's not saying that our surface area is 4 and our surface area is 9. It's just saying our ratio of those. All right, 6 says two similar cones have a radii of 9 inches and 12 inches. What's the ratio of the volume of the smaller cone to the volume of the larger cone? So again, start off with finding scale factor. And I'm going to actually let you find this on your own. So reduce it as low as you can. And then it says for volume. So when you find your scale factor, remember volume is the scale factor cubed. And there you'll have your answer. All right, number 7. The softballs below are similar spheres. If the radius of the larger softball is 1.9 inches, find the radius of the smaller softball. Notice here, they give you the volumes of each of them. Think about volume of a sphere is 4/3 pi r cubed. All right, that one's yours. Video's going on 10 minutes, so I'm going to let you guys do that one for tomorrow. See you.